In grade school, you were taught that you can't have circular definition. However, in elementary school, you are taught a whole lot of lies about mathematics, biology, and history. I'm going to show you why this has to be a lie and then give you a way to handle circular definition. Imagine you have a dictionary in a language you don't understand at all. You hear a word and look it up, but since you don't understand the language, all the words in the dictionary don't make sense. So you look those words up in the dictionary. You go from reference to the thing that was referenced, time and a time, replacing the words with its definition. Because the dictionary is finite, at some point you'll get to a word that is undefined, or you'll get into a loop of definitions. If your grade school teacher was right, then all the definitions in this dictionary would be useless. So that can't be what is happening. So how do we define anything then? Well, there is the boring practical answer. Dictionaries assume that you know some words, and then the onward expanding web of definitions will eventually catch a meaning of a word you already know. Basically, dictionaries allow you to take your existing vocabulary and expand it to new words. That's why dictionaries for kids have pictures. Kids don't have many words, but pictures allow you to step out of this web of words into a new domain. But I'm not about practical answers. I'm a mathematician who sometimes talks about art, logistics, computer science, philosophy, VTubing, graphics. Look, honestly, I do not know what I am, but whatever I am isn't practical. Also, this practical approach doesn't really spark joy in me. So is there another way to solve this problem? In mathematics, there are axioms. When you do the little kid thing of asking why to each explanation given, an axiom is where mathematics gives up and just says, just because. It is an assumption that you make to have a starting point. Oh, and I'll let you in on a little secret. What axioms you use are almost completely arbitrary. So long as the axioms you choose don't contradict with each other, you can pick any collection of axioms based on whatever reason you wish. Then you can explore whatever the mathematics arises from these axioms. But examples are good. Here are some of the axioms for the counting numbers, also called by some people the natural numbers. The thingy named 0 is a counting number. Technically, thingy is a referent, but I like thingy better because I'm a Perl programmer. There is a function, you can check my video about functions, called successor, which has the following properties. You can put a counting number into the successor function and you will get a counting number out. If two numbers are different, then they'll have different successors. 0 isn't the successor of any number. The successor function is like adding 1, but at this point, we haven't invented 1 or addition, so we can't actually talk about them yet. There is an induction. An induction is a way of taking a small proof and expanding it to cover everything. If something is true for 0, and if by assuming it is true for a number, you can prove it's true for the next number, then it is true for all the numbers. There are other axioms that define addition, multiplication, and ordering for the counting numbers, but you get the general feel of how the counting numbers are defined. Also, technically, the last thing with the induction is a schema, but that's a topic for a different video. This is what the counting numbers look like in this system. We can relabel these symbols, and as long as the relationships between the numbers are not changed, this type of relabeling relationship is called an isomorphism, which I get into in my function video again. But that's not the only way of resolving undefined terms. Here is a method that doesn't just avoid circular definitions, it embraces them. In order to explain it, I'm going to have to make a diversion into computer science. In a computer's memory, everything is just circuits that are either turned on or off, ones and zeros, bits. In order for these bits to convey information, you need to have a context which tells you how to interpret these ones and zeros. This context is called the type. If a pattern of bits is an integer type, then the computer will interpret this as an integer. If the bit pattern is a string of character type, then it will be interpreted as a sequence of letters. If a bit pattern is a color type, then it will be interpreted as a color. In mathematics, we study types using type theory. We can construct and define types in terms of other types using processes that are analogous to multiplication and addition and even functions. An example of this, say you had a system that stores photographs and you wish to include the location that the photograph took place. So you would have a record for this photograph which included a value that had a location type. But what if you didn't know exactly where this photograph was taken? Now, if your system was badly written, you could store the location as 0 north, 0 east. However, then how could you tell if this photograph was at an unknown location or what if it was taken at 0 north, 0 east? What you can do is create from the location type an optional location type. This type could either have in it the location or a special value called nothing. Because making things like this optional is such a common operation, languages often include a special function on types called maybe. Oh, and for variables, I'm going to use shapes with big holes in them, which sort of look like containers. I think it's a clearer way to represent that this thing is a thing that holds a value. Along with the type function maybe, these languages also provide useful functions. The just function gives us a way to lift a value from the base type into this derived maybe type. You also get an induction. An induction is a type of function which lifts an existing function on the base type up into the derived type. Give me a default value for the nothing case and a function that works on the base type, and I will give you a function that works on the derived type. Having things like this is really convenient because it means we don't have to keep re-implementing all the code to work on every optional type. But what happens if we use this maybe type in a circular definition? What if we say type n is defined as being maybe type n? Now, we can think of definitions in two ways. We can treat it as a replacement rule that says whenever you see n, then replace it with maybe n. Like you can replace bachelor with unmarried man. This is not going to work in our circular definition case because by replacing it in the string, we just expand off into infinity. However, there's a different way to think of a definition. We can think of it as constraints on what something can be. In other words, the definition creates a class of thing that obey a particular rule. In this way of thinking, the class bachelor is of all men who are not married. From this angle, our n is defined as maybe n. We are looking for a type that remains unchanged when maybe is applied to all of its terms. Let's work out what terms inhabiting this type are. We know that nothing has to be a term because all maybe types have a nothing term. If nothing is a term, then just nothing is also a term. If just nothing is a term, then just nothing is a term. And we go on. When something goes through a process and you get the same result back, that's called the fixed point of that process. Hold on, this type looks familiar. It's just the counting numbers with different labels. And how about our maybe induction? If we shift around a few symbols, that's just the induction for the counting numbers. Fixed points make circular definitions useful. Now, some people complain that women are people who identify as women is circular and invalid. But now that we know about fixed points, we can understand that this class is valid. It is the class that doesn't change when it passes through this loop. In other words, fixed point logic says trans rights. Thank you for watching. And if you enjoyed this bizarreness, please consider subscribing.